This is the introduction slide to the fluid mechanics project, where the title is Average Velocity in the Hose of a Vacuum Cleaner. Group 1 chose question 3.56 from the Potter textbook from the course. We first solved the problem theoretically and then experimentally. We were required to calculate the average velocity inside of a vacuum. First, we solved the problem theoretically. In order to solve the problem theoretically, interpolation must be done. In order to do interpolation, the following figures were used from the table from the textbook, as well as an altimeter on an iPhone 11. Using the figures from the table in the previous slide, interpolation was done to acquire the density and pressure at 1620 meters altitude. Once interpolation was done, we used these values to substitute into Bernoulli's equation. When using Bernoulli's equation, we also assumed that the initial velocity was 0 and that the change in height was 0. Then we isolated for the final velocity, and we obtained that the final velocity was 63.1177 meters per second. The experimental objective was to calculate the average velocity inside the tube of a vacuum cleaner. The following is a list of apparatus used in our experiment. The following is a step-by-step method approach to our experimental procedure. First, we attached the pipe to a vacuum cleaner, we turned the vacuum cleaner on, and we recorded a ball going through the tube. We did this 8 times, and then we calculated the velocity. The vacuum cleaner used was a Genesis Cyclovac vacuum cleaner, which is a normal household vacuum cleaner. Here is a schematic on how the experiment was conducted. At the top, we have the vacuum cleaner connected to a straight tube. The tube was needed to be bent in order to capture the ball going through the inlet and outlet of the tube in the same frame of the video footage. Here is a photo of the vacuum cleaner used. Here is also a photo of the tube inserted into the hose of the vacuum cleaner. This is very airtight, and we can neglect any air that might have escaped. Since the tube was quite bendy, we attached it to a stair railing in order to acquire a straight line distance of the tube. A kitchen scale was used to find the weight of the balls used. We could not find the weight of one ball used as it was too light, so we measured 11 balls and divided the mass by 11. Here are photographs of how the experiment looked in real life, very similar to the schematic shown previously. Multiple assumptions were made in order to conduct this experiment. Some of the assumptions were that the ball is assumed to move at the same speed as the air inside the tube. Another assumption is that the initial velocity of the ball was assumed to be 0. There are many more assumptions that we made in order to conduct this experiment. Since this experiment has to do with pressure, we know that altitude and temperature affects pressure, which is why it is mentioned under experimental conditions. Unfortunately, the experiment was not as precise and accurate as we had hoped. This is due to many things. One main factor is that we were not able to use a neutrally buoyant fluid, such as helium bubbles. This could have been obtained by suctioning helium bubbles through the tube using expensive equipment such as a very bright source of light to monitor the helium bubbles. Unfortunately, we were not able to obtain this equipment, and we just used an ordinary ball. Here is a video of the experiment at normal time. Here is a photo highlighting the ball entering and exiting the tube. In order to solve the problem experimentally, we used the following formula, where V average equals the total distance over the elapsed time. We also calculated the density of the ball to show the following. We can see that the ratio of the density of the ball to the air was 1056,74. This will show that a huge error was caused since the ball was not a neutrally buoyant fluid and so much more dense than air. Once all the videos were captured, we slowed the playback speed by 100 times. We then recorded how long it took in slow motion from the inlet tube to the outlet tube for the ball to pass. We took this time and divided it by 100 to get the time it would have taken in real life. Here is a table summarizing the 8 runs with the time in slow motion and in a normal time reference. We used those 8 recordings to calculate the average time it would have taken a ball to go through. We used this time and the displacement of 4 meters to calculate the average velocity of 11.8081 meters per second. We then used this value and the theoretical value achieved in the beginning of the presentation to calculate the percentage error. We then used that velocity of 11 meters per second and substituted it into Bernoulli's equation. Firstly, we used the density of air at an altitude of 1620 meters. We acquired a pressure of 10.4338 pascals. This is a strange answer because the pressure should have been negative due to the suction of the vacuum. When we repeated the experiment with the density of the ball, we got minus 76,969 pascals. This is also very strange. Although the sign is correct due to the suction, this is a very large number, and the real number would be a negative number that should be a lot less in magnitude. The following is a summarized table comparing the theoretical and experimental values as well as the uncertainty calculations. There's a very big discrepancy between the theoretical velocity and the experimental velocity, and a percentage error of 81% was calculated. We have concluded that this error and the discrepancy between the velocities is mainly due to the fact that the ball is not a neutrally buoyant fluid, and that the experiment would have been a lot more accurate had we used a neutrally buoyant fluid like helium. Even if we didn't use a neutrally buoyant fluid, the experiment could have been more accurate and more precise had we increased the amount of runs taken and had we used a less dense ball. Here is a link to extra files containing all the slow motion videos, the normal videos, and this presentation, so you can go through it at your own pace. Here is a slide with all our references. We hope you enjoyed our video. Thank you very much.